That is called graphitization. Because mostly we are studying about iron cementite metastable phase diagram. But if you want to study iron carbon phase diagram, then you need to have pure carbon and iron on. You don't have to have any kind of cementite in your structure, right? Only iron and carbon. And two things if you remember, we have discussed about you can directly convert liquid iron into iron and carbon. That is called, remember, primary graphitization, right? And we can have secondary also. Secondary means once we convert our liquid iron into solid iron, and you have gamma plus cementite, for example, you can convert cementite into iron and carbon further. Yeah, that is the secondary graphitization. And also you remember that basically cementite is very hard and brittle structure, right? And you can change the shape of the cementite also. You can make it into nodules, which is bringing ductility into your material, because most of the cementites are in needle form or like flake form kind of. So you can convert it into round shape, spherical shape. That is called spheroidization. And that iron is called spheroidized graphite cast iron, SGI. But in the coming lecture we will discuss how heat treatment will help you to do that also. If you have cementite and you want to change the cementite into nodular shape, you can do some heat treatment without doing anything else. Right? And also we have discussed about alloying element which stabilize graphite, if you remember. Right? Silicon, nickel, aluminium. If their concentration is high, you can directly form iron and graphite. Instead of cementite, you can directly form also iron and graphite. And graphite will remain in carbon can remain in two forms in iron carbon system. One is graphite, pure iron, one is cementite. Right? And graphite can exist in form of nodular shape or maybe flaky forms. So already we have discussed that, everything. Right? So that's why we can have, if you remember, grey cast iron and white. There are two types of basic cast iron, grey and white. Right? How we can distinguish them, grey and white? Just fracture them. Take the piece of cast iron, you fracture it, you break it, and under the microscope you can see white layer of the fracture surface will appear as white. That is actually white cast iron. If it will appear as grey, the fracture surface, it is a grey. Why this is happening? Because of the presence of cementite. Because white cast iron, carbon remain in combined form, that is cementite. But in grey cast iron, carbon remain in free form, completely pure carbon, that is graphite. That is the reason. Right? So two-way carbon can exist. One is either pure graphite or maybe combined cementite. So white cast iron, if you look, you have cementites mostly. Iron and cementite. Maybe perlite and cementite. Okay. And if you check grey cast iron microstructure, you will be having flakes of graphites mostly. That means pure carbon. Anyways, we will not discuss that. This is important now. You may get question during your placement also. Effect of alloying element on iron carbon phase diagram. So they can ask you like this: draw the iron carbon phase diagram and discuss if you add a certain kind of alloying element, what will happen in the iron carbon system or in iron cementite system, what will happen? What kind of changes you can see? Suppose I am adding chromium into iron cementite phase diagram. What will happen to the iron cementite phase diagram? Right? If I am adding nickel, so what will happen to the iron? You can draw the diagrams or you can explain them, whatever. Okay. So this is very important. Nickel. And this will also help you to decide the heat treatments also. Okay, let me draw the quickly iron carbon phase diagram. You can draw it. Can you draw the iron carbon phase diagram quickly without representing any kind of phase? Just draw it. anyways?
White color card.
White color, I think white color. Otherwise it's fine, at least. Right? So you just see, we have, this is one important point. This is which point, you remember? A3. And this is another important point. This one? A1. Very good. And there is another important point. A4. Right? These are three important points. What kind of points? These are critical points actually. But if you say temperature, then critical temperature. A1 is the lower critical temperature, A3 is the upper, and A4 is the temperature where you have again delta. Above A1 you have austenite, above A3 you have austenite, but above A4 you have ferrite, which is BCC, because this is gamma. So largest region in the iron carbon diagram is the gamma region. You see FCC. The largest region in the iron carbon diagram is FCC. Right. So this is interesting actually. There are certain kind of alloying element. If you add into iron cementite system, they can shrink the ferrite and the ferrite. They can shrink the ferrite, but they can expand the gamma region. Just opposite. There are certain kind of alloying element. If you add in iron cementite system, they will expand the gamma region, but they will shrink the ferrite region. Okay, just opposite. So one kind of alloying element will expand the gamma region, but they are shrinking the ferrite region, and there are certain kind of alloying element which will expand the ferrite region, but shrinking the gamma region. Just opposite. So that on that basis we can have two kind of alloying elements. One is called ferrite stabilizer, one is called austenite stabilizer. So this is the thing. Ferrite stabilizer versus austenite stabilizer. So first difference you can easily write. That means they will expand the ferrite region but shrink the gamma region, austenite region. Here just opposite. Austenite stabilizer will expand the gamma region but shrink the alpha region or ferrite region. So you can write very simple, nothing to do. Now people basically in GATE exam many times they ask this question. Give some example, or you can join ferrite stabilizer with alloying element and austenite stabilizer with a particular alloying element. Many questions are there in GATE exam earlier. So best example of ferrite stabilizer is your chromium. Chromium, tungsten, right? Alloying elements are what? Chromium, tungsten, vanadium, niobium, silicon. These are ferrite stabilizers. If you add them into iron carbon system or iron cementite system, that will expand ferrite but shrink the, actually it depends upon amount and the strength also. It depends upon amount and strength of the alloying element. If you add lot of ferrite stabilizer, you may end up in a situation where there will be no austenite phase. If you heat, basically what do we know? We start the sample from room temperature, we take the piece of steel and we will heat to the high temperature, and we can go to the melting point, and we can see different structures. Room temperature is BCC, then we get FCC, then again BCC, then liquid finally. This is the thing, no? Right? But if you add lot of ferrite stabilizer together, you will not get any kind of, maximum chance you will not get any kind of austenite in the structure. That means even at high temperature you have still ferrite. That means austenite is gone, kind of. It's not exactly true, but it will be gone. You cannot able to get austenite in that condition. So my point is, if the amount of ferrite stabilizer is too much in the steel, you cannot get austenite. From room temperature to melting point, you have only ferrite. Throughout the temperature, you have only ferrite. That is actually technically they call formation of gamma loop. A small loop of gamma will form. See, the gamma is too much big. Gamma is too much big. Whenever you are reaching here, you are getting gamma continuously. But this will shrink like this and this will shrink like this. If you have too much alloying element of ferrite stabilizer, this will shrink like this and this will shrink like this. And finally it will end up with like this kind of structure, this kind of loop. A small loop will be there. I am not drawing it, but a small loop will be formed. That is called gamma loop. So throughout any temperature you will have only ferrite. So technically what it means, top part is delta ferrite, bottom part is alpha ferrite. That means they are coming closer with one another, they will merge, right? So in other way what I can say, just see I have written changes the critical points. It means the A4 point will go down and A1 point will go up and they will finally meet, and everywhere you have ferrite. Whatever you do heat treatment, you will not get austenite. Always ferrite will be there. So in simple word you can write second point, critical point change. How the critical point change? If you add lot of ferrite stabilizer, the A4 point will go down and A3 point will rise. And lot of alloying element means they will merge. They will become a single point at the end. And you have only a loop, that is gamma loop. Do you got the point? This will go down actually, slowly go down, and this will go up. And finally they will merge. But rest portion is your gamma, little portion, that is called loop. But here you have only ferrite. Just opposite. You add lot of austenite stabilizer. So what will happen to the critical point? Now you tell me. Just think and tell. Just think. Just instead of ferrite stabilizer, you add lot of austenite stabilizer. What will happen to the critical points? A4 point will go up, A3 point will go down. Very good. Because that will stabilize gamma, that means it should be expanded. So A3 point will go down, A4 point will rise. If you add too much of austenite stabilizer. Okay. What are the alloying elements? The major alloying elements are nickel, very strong austenite stabilizer. And the cheaper one is manganese, very cheap. And you can add cobalt, you can add also copper some amount. Actually, these are more soluble in steel, but cobalt and copper solubility is not so high actually. Is it fine? So these are alloying elements. Sometimes they may ask in the interview also. Just give two examples of austenite stabilizer. You can give nickel and manganese, but nickel is expensive. Manganese is cheaper. But copper and cobalt is also expensive. Copper is cheaper somewhat, relatively cheaper, but the solubility is less. You cannot add too much of copper because its solubility. Because we know that no, we can have two kind of solid solution. One is interstitial, one is substitutional. So all these alloying elements are basically which kind of? Substitutional, not interstitial. They are very big. Substitutional solid solution will form when the size of the parent atom and the solute atom are comparable, similar size nearly. Or if there is a difference, a little difference should be there. How much? 15%. For extensive solid solubility, you should have 15% in the difference in the size. Diameter or radii, whatever you can say. And what are the other points? This is a question they ask sometimes. They should have same crystal structure. Electronegativity difference is also there. The first condition is size factor, right? Size factor means the parent atom size and solute atom size should be comparable. If there is a difference, the difference should not exceed above 15%. Otherwise, it will not form solid solution. Okay. Second point is crystal structure should match. The parent crystal structure and the solute crystal structure should be nearly same. Second. Third is electronegativity. Electronegativity difference is too much. Then it will form a compound, not a solid solution. But electronegativity difference is less. It will. You understand like Fe3C. Fe3C means carbon have some electronegativity, iron have some electronegativity. Difference is too much. That's why Fe3C is forming. It is not a solid solution. But if you add in a small amount, it will form solid solution, but interstitial, not substitutional. Anyways, for example, iron, aluminium sometimes also form intermetallics. Aluminium, iron, intermetallics is sometimes formed. You can see. Anyway, we will not go into that. Like sodium chloride. You add sodium and chlorine, it will form NaCl, but it will not never form any solution. Where the electronegativity difference is too much. How you decide electronegativity difference? If you take one element from the right side of the periodic table and one from left side, and far apart, then it will form compound, not solid solution. Solid solution means alloy basically, completely soluble. Anyway, the last one is electronegativity factor is there also. Electronegativity means that is actually what called like Al3 positive. What is that? Valency factor. Yeah, valency factor is there. So which one is more soluble in which one? Lower valency is more soluble in higher valency, or higher valency is soluble in lower valency? Which one is true? Higher valency always become more soluble in lower valency. You have to remember. Like copper and nickel. Or copper has one. Copper has one. Nickel has two kind of. Aluminium, copper and aluminium, for example. Copper has one. Aluminium has three. So copper is more soluble in aluminium, but aluminium is less soluble in copper. One example. So these are the 4 points. Anyways, we will not discuss that. But my point was all these alloying elements are substitutional, bigger size. They are not interstitial. But carbon is also a very strong austenite stabilizer. But that is an interstitial atom, not substitutional. Similarly, nitrogen also. So carbon is a austenite stabilizer, nitrogen is also austenite stabilizer. But they are interstitial, not substitutional. But we are discussing about substitutional mostly. Okay. But you can see this is what is the crystal structure of cobalt. Cobalt is FCC. Cobalt is FCC or BCC? You are guessing. But I remember FCP. Just check one. Just once check. I remember FCP. BCC, it is not BCC at all. FCP. But if you take it to high temperature, it will become FCC. So that is a term you people have heard maybe. Superalloys. Have you heard about superalloys anytime? Superalloy. So they are certain alloy, they are like Superman. They can withstand very high temperature. They will not fail. So these are the three elements. One is iron, one is cobalt, and nickel. That means you can have iron based superalloy, you can have nickel based superalloy, you can have cobalt based super. These are the three elements. Why? There is a reason. You can see iron is BCC at room temperature, but if you take it to high temperature, it becomes FCC. Similarly, cobalt is FCP, but you take it to high temperature, it becomes FCP. Nickel is always FCC. At high temperature also FCC. So all high temperature phase are FCC in superalloys. That is the main important. Why? Because FCC is a very close packed structure. No, atomic packing factor is how much? 0.74. Closed packed. The atoms are very close packed. How much atomic packing factor? 0.74 or 74% you can say. What it means? That means diffusivity will be high or less? Less. So diffusivity will less means failure will be taking more time. It will not fail. Because of diffusion, materials fail sometimes. That is called creep failure. You have heard maybe. There is a failure mechanism called creep. And that occurs sometimes due to diffusion of atoms or diffusion of vacancies. Have you studied this one in DBM maybe, I guess? Creep failure. Just introduction. Anyway, just remember this. Because high temperature failures are mostly by creep mechanism. There is a failure called creep. And the interesting point is the load which you have applied to the material is below yield strength. But still it will fail. Very interesting. You don't know, plastic deformation will start from the yield point, no? where the load will be reaching to the yield stress. Above that stress, plastic deformation will start. But creep is a plastic deformation, but it happens below yield point. But the temperature should be mostly high, and you should have given lot of time. Then only it will fail. So creep failure is a very slow failure, and it is catastrophic also. Catastrophic means you will not get when the failure will occur. It will automatically fail. That will not give you any kind of indication that I am going to fail, but it will fail. Suppose this breeze is going to collapse. It will first bend. Then further it will collapse finally. But it will not collapse directly. It will bend. That is, creep is not happening. How this will happen? If you apply load and that load is above yield strength, then only the failure will occur, the breeze. But if you apply a very high temperature to the steel and you are just giving tensile stress on it, but the stress is below yield stress, still it will fail. And that is creep mechanism. You understood why superalloy? Superalloy means they have FCC crystal structure at high temperature. And FCC is very close packed structure, so diffusion will be very slow. If diffusion will not happen, creep will not happen. That means Do you got my point? That's why they are superalloys. If failure is, that means you can what I can say, you can increase the life. It doesn't mean creep will not happen. Creep may happen, but after a very long interval of time. Suddenly it will not happen. That is the reason. But if high temperature structure is BCC, then what will happen? Creep will happen easily. BCC is very open. No, how much? 68.68%. No. So it is open. Open structure means diffusivity will be easy. Lot of available space are there. Atoms can easily move. That's why I talked about, if you remember, diffusivity and solubility are two different things. Never confuse between diffusivity and solubility. Solubility always depends upon the size of the voids, interstitial voids. More is the size of interstitial void, more is the solubility. Right? Or it also depends upon the temperature. If you check delta ferrite and room temperature alpha ferrite, carbon percentage is higher in which case? Delta ferrite. That because delta ferrite is a high temperature structure. So if you take same ferrite but at high temperature BCC, solubility is more. Why? Because expansion will be there. The moment you take something into high temperature, there will be expansion, so void will also get expanded, so more carbon can go and stay there. So these are some important points. Solubility always depends upon the size of the void and temperature, basically. But diffusivity depends upon openness or closeness. If the crystal structure is very compact, like FCC or HCP, diffusivity is slow. If structure is open, diffusivity is fast, like BCC. So these are very important, always remember this. Anyways, we will not go into that. So these are examples. Next, another important point is, this ferrite stabilizer, solubility is very high in alpha iron or in ferrite. Just opposite, that means austenite stabilizer, solubility is high in gamma iron. Right? Depending upon the solubility, you can write also. That means if you add austenite stabilizer in ferrite, solubility will be very less. Just opposite. If you add ferrite stabilizer in gamma iron, solubility will be also very less. Just opposite. So one is solubility, one is A1, A3 changes, already I discussed. You can write two. And you can write one important point, that is 12.5 weight percentage carbon plus other alloying element like chromium. Sorry, this is chromium. Chromium, and this is tungsten, vanadium, silicon. If you add all these alloying elements, and the amount of alloying element, that is chromium, is 12.58%, you have only ferrite in the steel. Even at high temperature, you have only ferrite. I don't remember exactly the composition of tungsten, vanadium and silicon. See, all are ferrite stabilizer. But amount of chromium is too much high, 12.5. Because those are ferrite stabilizer. For actually, basically, most of the chance what happens, ferrite stabilizer are those alloying elements, their crystal structure is matching with the ferrite. Ferrite is BCC, and if you check the crystal structure of tungsten, chromium, vanadium, they all are BCC, except silicon. Crystal structure is matching. So that's why they are stabilizing that one. Okay? Silicon, which kind of crystal structure? This is an exception. This is silicon is diamond cubic, but chromium is BCC, tungsten is BCC, vanadium is BCC, niobium is also BCC, and silicon is just diamond cubic. So in other word, I can say, just see, nickel is FCC, manganese is also FCC, chromium is also FCC. So austenitic stabilizer are those elements whose structure is FCC, similar to that of gamma iron. So that's why they are stabilizing, because of same crystal structure mostly. But certain exceptions always exist, like cobalt and silicon. Okay, you can write one last, this one. Change the carbon percentage in the eutectoid steel. So you can write one important line, whether it is austenite stabilizer or ferrite stabilizer, whether it is ferrite stabilizer or austenite stabilizer, they always reduce the amount of carbon in eutectoid steel. Whether it is ferrite or austenite stabilizer, they always reduce the carbon in eutectoid steel. they always reduce the carbon in eutectoid steel or eutectoid composition, whatever you can write. If there will be a question, what is the effect of ferrite stabilizer on eutectoid composition? You can simply write the carbon percentage will be lower. Same, what happened to the, if you add austenite stabilizer, what happened to the eutectoid composition of the carbon? It will also reduce. So one point I can simply say, you just check the ferrite stabilizer alloying element and the relationship with carbon. Can you check? What will happen if chromium will be there and carbon will be there? And what will happen if tungsten will be there and carbon will be there? You know that. They have very high affinity towards carbon. So you have to remember, austenitic stabilizer have very high affinity towards carbon. So what will happen? They will form a compound because of high affinity. So you can have tungsten carbide, you can have chromium carbides, you can have vanadium carbides, you can have niobium carbides, silicon carbides. All will form stable carbides. And carbides are what? Precipitates. They will provide you very good precipitation strengthening. But this austenite stabilizer, they have very low affinity towards carbon. They will not form any kind of carbides. Nickel don't form any nickel carbide. Manganese don't form any manganese carbide basically. Cobalt also don't. Copper also don't basically. So austenitic stabilizer are not forming any carbides. But ferrite stabilizer will form carbides mostly. So that is one of the reasons why carbon percent will go down. You understand my point? Because carbon is free now. Suppose you take austenite phase. Okay, just you take austenite phase. Austenite phase means everywhere you have grain boundary. Nothing else is there. Everything is soluble. It is a single phase solid solution. Interstitial solid solution. Everything is soluble. Right? Everything is soluble. So carbon percent is very high. But if you have ferrite stabilizer, the ferrite stabilizer will attack the carbon and take away the carbon from the austenite. It will form carbides. That is my point. So carbon percent will go down if you have ferrite stabilizer because they form strong carbides. And that is also good. You can have precipitation strengthening. But can you tell me, okay, there is a kind of strengthening called dispersion strengthening also. You have heard this one? Never heard. Why? How? DBM, some might have taught you mechanism, different strengthening mechanism also. Solid solution strengthening, grain boundary strengthening, right? Phase transmission strengthening, strengthening due to solid solutions, strengthening due to precipitate, strengthening due to dispersed soil. You don't know these things. How? Hey, this is a very important question in the placement, right? Different strengthening mechanism. They ask what are the different strengthening mechanisms in steel. We have to explain. Okay, let me tell you very short right now. See, there is a kind of strengthening called dispersion strengthening. That means in that steel or in that particular alloy system you have dispersed soil, not precipitate. Those are dispersed soil. Dispersed soil is a foreign particle. For example, alumina, Al2O3. Al2O3, you are adding Al2O3 particle into the steel, for example. So Al2O3 is a foreign particle. Steel is iron only. That is a dispersed soil in the iron matrix. But suppose you are forming Fe3C. That is not a foreign particle. Because of carbon in the iron is reacting with carbon to form cementite, Fe3C. That is a precipitate. But dispersed soil is alumina. That is a foreign particle completely. Similarly, you can have yttria also. Yttria means particles of yttrium oxide. Y2O3. That is also a foreign particle. Those are dispersed soil. The advantage of dispersed soil is what? The creep resistance will be maximum in dispersed soil. Why? Because dispersed soil are foreign particles, right? They are not the particles from the matrix. You have added it in separately into the matrix, right? So they will not get coarsened. Coarsening of dispersed soil will never occur. But precipitate may become coarsened with time, with temperature. So you understood, if precipitates are very fine and in another steel you have same precipitate but bigger size, which one is good? Precipitate of small size are very good always because dislocation will interact more with them. But bigger precipitate means there are a lot of empty space will be there. Dislocation can travel to a long distance. You understood my point? Because volume fraction is same. Just you have bigger, you have smaller. Smaller precipitate means lot of precipitates will be there. When dislocation moves, it will suddenly interact with one precipitate. Again it want to move, again another precipitate will come. So lot of precipitates will be there. But if the size is bigger, you have lot of empty space will be there, right? So dislocation will find lot of time to interact with them, right? So obviously strength will be less. So same thing happen. If you are taking your steel to high temperature, precipitate become bigger with time. That is called coarsening of the precipitates. So what will happen? The strength will go down. The creep resistance will go down. But if you have dispersed soil, they will never grow. They maintain their size on this because that is a foreign particle, so they will never grow. I think sir might have taught you maybe in phase transformation. I am not sure. Coarsening of the precipitates. Sir didn't talk about that. Coarsening phenomenon he might have taught you due to diffusion. Oswald ripening he might taught you maybe. Cutting bypassing okay. Auroral mechanism and shear mechanism. So DBM report आई तो मतलब ना भूलिए. If precipitate is very small, dislocation will shear it, cut it. If precipitate is bigger, then it will bypass. It will make a loop and bypass it. I don't know how you should know these things. These are very important. Anyways, you understood what are the. So we can have ferrite stabilizer, we can have austenite stabilizer. So they will change the critical points. They will also stabilize one phase and destabilize the other phase, kind of thing you can write. And okay, last point I will discuss. Similarly, if you add lot of austenite stabilizer, at room temperature you have only austenite. In the middle portion you have austenite. At high temperature also you can have austenite. Everywhere you have austenite phase at any temperature. Condition is you can add lot of alloying element. Those are austenite stabilizer, like nickel. Okay, I have one question from my side now. Suppose you want to increase the strength of the steel and you want to do some heat treatment. Let it be. That is the patient. But now you are getting a steel which have lot of ferrite stabilizer now. So what can be done? Again I am saying, listen it carefully. You got a steel and that steel have lot of ferrite stabilizer. What it means? At all the temperature you have ferrite, you will not get any kind of austenite, okay, right? But still you want to do some heat treatment and you want to get some benefit out of it. So what can be done? Grain size decrease. Okay, forget about grain size decrease. You got the question or shall I repeat? Because most of the heat treatment we are taking the steel to the austenitizing region, but there is no austenite. Even if you are heating the steel to high temperature, you have ferrite. And transformation will never occur. Ferrite to ferrite transformation will occur, right? But if austenite will be there, you can transform it to benite, you can transform it to martensite, whatever requirement you want, you can got it. But what is the solution? Forget about grain refinement. Yeah, that is also good. You can increase the toughness. What is the solution? Simply add a small amount of austenite stabilizer, little amount of. Like you can add 2% of austenitic stabilizer having 18% of chromium. There is an example, very good example. You have a steel and you have 18% chromium. That means it is strongly ferritic steel. And you cannot do heat treatment on it. You can do what? You just add fresh alloying element 2% of nickel. Some austenite phase will appear. That means some region of austenite will come out. And you can do heat treatment on the basis. But there is another solution also. Suppose you don't want to add any alloying element. You have no option. You cannot add any, that means alloying element addition means you need to melt it first. Then only you can add alloying element. But your boss say, no, we don't want to melt it. You have to increase the property. What can be done? Still you have to do heat treatment, but what can be done? One point he told, you can refine the grain size by doing faster cooling from high temperature. Anything else? We can go for rolling, cold rolling. Cold working, you just do the cold working on it and you can do annealing on it further, right? That is called cold working annealing cycle. Cold working करोगे तो क्या होगा? Lot of strain will generate, dislocation will generate. That is called dislocation strengthening. That is the simple answer. Just go for cold working. Similarly, I told answer like you have pure aluminium, you have pure copper. You cannot do any kind of heat treatment to improve the property because phase transformation is not happening. Everywhere FCC is there. What can be done? Go for cold working. Just roll it. But below the recrystallization temperature. That is called cold working. you can increase the strength to a very high level just by introducing lot of dislocation. So my suggestion is, please go through the strengthening mechanism. If you carefully look this physical metallurgy and mechanical metallurgy, everything finally finish at strengthening mechanism. Whatever you are discussing, it may be dislocation interaction, dislocation precipitate interaction, whatever you are studying, jogs, fluid dislocation, whatever, finally they will end up with your strengthening, how you can improve the strength. Okay, then can you tell me, by doing heat treatment, how we can achieve very high strength? We are not doing any kind of cold working, we have only option to get high strength, but you have to do heat treatment. You have to do quenching, very good. You take the steel to the austenitizing temperature and quench it, suddenly cool it. You will end up with martensite. So that is the answer. That is called phase transformation strengthening by forming martensite. That's why we are studying heat treatment. We'll discuss that, hardening heat treatment. Okay, we can end.